We had seen then this last equation that allowed to describe the biological activity in terms only of pi. That was pi, the lipophilia, of a fragment very well. Then we had seen that the activity is inversely proportional to the lipophilia of the fragment pi. Therefore, on the basis of that, we had reached the conclusion that one of the best groups was a hydroxyl, since it provides a negative pi, and here we had to choose if we want the aliphatic contribution or the aromatic contribution. That is why we selected the second, the contribution. In this case, the certain aromatic, because the hydroxyl is connected to an aromatic ring. And with that, we calculate the predictive value of biological activity. And it gave us the order of 6, that is the micromolar order. Look how interesting it says here, 2 electronic effects, a QSAR equation with the constant of Hammett. Well, first, let's remember some particular things. If we go to the up, we have the dissociation of benzoic acid. Remember that this model is the empirical model for the determination of a constant of Hammett. And ask what the constant of Hammett measures with positive values if the substitute is electroattractor or electric attractor. Very well. And if the negative measures if it is an electrode, that would be the most correct terms. And the constant of Hammett, here is the definition of the sigma, is defined as the logarithm of the dissociation constant of benzoic acid, when it is the substitute x, and when it is not, or what is the same, logarithm on base 10 of the constant when the substitute is less the dissociation constant of the ray benzoic acid. Asks the constant of the substitute of Hammett measured in this empirical way in which positions is valid. That is the value of sigma, calculated according to Hammett, for which positions in an aromatic ring any is valid for and end go. Very well. That is, we can measure the effect in position, for we can measure the effect in position go, any of the 2 positions go, but not in ortho position, because if the substitute is in ortho position, no longer only primates the electronic effect on the dissociation of benzoic acid, but also primates the effect that happens. Sorry, the thing is already out there. Look, if this is close, what can happen? Certain stereospatial interaction between a group and the other. We agree, therefore, to prime the steric effect. Then the constant of the substitute of Hammett empirically measured is for gold positions and position 4. We cannot determine the effect in ortho position because it is not an electric attractor effect or pure electrician, but it is also mixed with the steric effect. I am going to give you an example. Allow me, we are going to illustrate this point. It already asks. Then we have our benzoic acid as a reference system. We are going to have these 2 systems. The benzoic acid replaced with these 2 groups. Replaced with the group CMN and replaced with a hydroxyl group. Then in which of the 2 the sigma of Hammett is positive? Well, here it is not true that for no link electronics in both cases, the 2 groups are clearly different. One is going to be positive and the other negative. The hydroxyl is the electrode. And how is this group called? And very well, the CN group or nitrile is the nitrile group, and the nitrile group is very good. It is an electric attractor. So this is an electric attractor, very well. And the other is the electrode. Perfect then in conclusion, as they have just told me in A first case, the sigma is positive, while in the second case it is negative, which is an electrode. The first is an electric attractor only by inductive effect. It also has resonance, resonance. It is not true that there may be resonance here too, but since a double link can come out on the system, instead here, an electronic pair enters the system, and based on that, the question that I am going to ask you now is the following. Which of the two systems has a greater constant of acidity? Or in other words, because you are more familiar with this concept that is studied a lot in general chemistry in introductory courses. In this case, call me this one and the other in case of which is less the first or the second, yes. But it has already been with him. It is more acid. Be careful because the electric attractor, what it will do is better. Stabilize the negative charge that is generated when the proton is released. The conjugate stabilizes better in the first case, and therefore the first acid is more or less acid, more so perfect, and as it is more acid, U.S. Exactly. Therefore, it is large. Very well. Very well. In this case, it is less numerically speaking, and I am going to give you the values. We are going to take advantage of the fact that we are connected to give you the exact value according to literature. According to literature, this thing is 4. 2. It does not open for 3.55. So let's go over here. I'm going to write down the value. It's 3.55. Let's go to the second. According to literature, the para has a value of 48. The position for hydroxyloid is therefore 48, already 48. Then it makes sense, of course, because having an electric attractor we have that the acid is increased. And now, how much is the value of the sigma constant? As we can know the value of sigma, we cannot know it directly too. We have to do the subtraction. Well, we go to the value of the benzoic acid, you will say, but teacher, you already gave us a website where we can see it quickly. But I want you to do it by hand, so to speak then for T. We need the QSAR of the pure benzoic acid. According to literature, the pure benzoic acid has a value of 4. 2 already perfect, more than sufficient. Then we go there and then I'll reference the QSAR. I repeat, the pure benzoic acid, that is, when the substitute is H is equal to 4. 2, and that 4. 2 is in between this value, is in the middle of 3.55 and 4.48. It already makes a lot of sense then. Now we can calculate the sigma of the hammer. We are going to do it by hand. Then we go to the first case. We already have that in the first case, the sigma of the molecule A. We call it so we already know that it is a positive value. It would be according to what we were seeing. Just here is the table log kx minus log k. Then it would be log sub x minus log k sub OK. According to this then, we have that the sigma would already be equal to the logarithm of k sub x. Well, that is the same as saying less the value of pk QSAR, because pk QSAR is not true. It is less logarithm, you understand. And then it says their logarithm, you understand. As the caches is more pk QSAR, when it is without any substitute. Therefore, in this case, it would be minus 3. And I do not know if I did something wrong. It is fine, they gave me a super negative value. And I had to give them how many positives, so we are doing something wrong. Correct me, please. We are going again. Then it would be log kx. When it is the substitute, it would be then, if I have a pk QSAR is a less logarithm, then I have to apply negative value and 355 negative minus. That is, it would be more the pk QSAR. There is more pk QSAR, sorry. It would be more 4. 2. There was the error. And then, because pk QSAR is 4. 2. There, it is well then that they are helping me so that we all reach the same value. We have the same value. With decimals and everything to 0. 14. I'll die. How? We agree then, that is the first value 0. 65. And from there, I am going to explain what happens in the other positions. And that is why I want to do this complete exercise. Always these things by hand generate a long-term cognitive impact. The cell by hand, and I hope that you do not forget more than positive means that it is a attractor group. And look, I am going to give you a mnemotechnical rule. Observe the following when one has the word attractor. Attractor. That is, with more the T is. Not true. Instead, Dado does not have their negative by default, so that he does not forget more than when it is positive, the group is attractor. We go to the second computer. We go to the second computer. Now, if I am going to move the image a little, for when it is with hydroxyl, then we move a little this, and we have that sigma B is going to give negative. Then it would be less the pk, so it would be less, and therefore that would be plus 4. 2, and then we have that sigma B that is going to give us negative is equal to decimals, and all that gives me 0, 28, not R minus 4 PC. Nita tilt, I was your Daxton, bottom decades, or the. We already have two values, stan minus 0, 28, and plus 0 delta. And pli io did tune turn the foundation dot to car. 65 calculated by hand, calculated by you with empirical values. Where I want to take them to these values, these descriptors were originally calculated in this way, empirically then, each physical chemical variable in theory must be able to be calculated empirically, only that today we have tables. And everything is already tabulated, therefore, when you go to paddle now, what paddle Well, here then, we have the system, it says R, and therefore we have to simply draw the group that we want to predict. In this case, the group is a CN. Therefore, we draw a carbon. Now we draw connected to it. It did not work like A. This we go again. We draw a carbon, but a carbon, I said. And now, yes, Then there we have the C and calculate. Let's go there. Let's see what this approximation tells us. Says that the sigma empires is 0,618, and it only gave us 0,65, quite decent already. To do a quick calculation, we go to another group. Then remember that value was 0,618, and to us 0,65, and with hydroxyl now direct there, the hydroxyl with hydroxyl gives less for less 0.30, exactly less 0.3, and the empirical is less 0.28 also again. It is a good approximation. It is not bad, therefore, we are quite well already. This type of, let's say it like that, online systems have already been published. This is not something key that any person uploaded, but there is always a platform and a paper that supports the in different goals, because the effect that primates in the case of goals is the effect to the inductive tractor. Then, as the hydroxyl group approaches, in this case, I did not have, that the resonance effect worsens the stabilization of the conjugate base. Better look, I explain it here, because that question is relevant, because in a positive goal, look, in the particular case of benzoic acid, we have this situation. Remember that what is happening is that the acid is acid as it ionizes. Then, when it ionizes, we have this situation, and here a hydroxyl group, well, one of tioxyl. Possible resonances for this hydroxyl group leaves just the negative charge inside the carboxylate. That is, there is a form of resonance that drastically worsens the stability of the conjugate base because it worsened. Because I say that it is getting worse in this case. Because we have, but what happens is that oxygen is always going to be positive. The problem is more here. Look what has happened. Instead of dislocating the charge, I mean the negative charge, because the starting anion is the charge and this starting anion has a charge -1. Only then, this form of resonance, instead of stabilizing this negative charge, has worsened the environment, putting another negative charge in the vicinity. Then I have two negative charges together, and that is stable or unstable, unstable, tremendously unstable. That is why a hydroxyl group in para has a negative sigma, because it worsens the stability of the conjugate base. It is a very strong electronic donor. However, this effect that I just explained does not exist when we are in meta position. When we are in meta position, you will say, but the conjugate base is formed, and there must also be some type of resonance. And of course, yes, but when we are in meta position, the resonance of the electronic pair moves. The resonance does not reach the carboxylate, but it is on the outside. Therefore, it does not destabilize it as in the position. For the negative charge is outside the system, then the negative charge was outside. It was not in the carboxylate itself, as in the first case. Then, if the negative charge was outside, it means that the resonance effect is not destabilizing it, that it is priming. When the oxygen approaches upwards, on the other hand, it begins to prime. When the oxygen approaches upwards, the inductive effect, the inductive electric attractor effect, inductive electric effect. I know that this is a bit abstract, and to understand it is better understood when one sees quantum chemistry, because there one separates the effects there. One has the molecular orbital of the complete molecule, and you who can draw the map of molecular electrostatic potential of the complete molecule. Of course, that does not imply a level of calculation and more fine understanding there. Then the explanation of why the sigma. When we are in meta, the sigma is positive, slightly positive, mainly by the inductive effect. And I have the third case left. And that is what I wanted you to be able to also visualize now. And why did we say that this sigma Hamid cannot be determined in an ortho position? Example we are going to see here. We have a hydroxyl in an ortho position. This molecule exists. You know it. And you are probably taking T from that it is called salicylic acid. It is more common to sell it in creams, shampoos, that type of thing because in tea or infusion. It is not recommended. It is an analgesic. It is not the salicylic acid. It is similar. It is missing only an acetyl. It serves as an analgesic. It serves as an analgesic because the problem is that it is very gastrolytic. Damages the stomach mucosa a lot. So it is not very recommended. It is very, very ulcerogenic there, as it is if you do the resonance of the. And then we are going to eliminate the group. First, allow me to erase up here. I am going to draw the anion now, so that we agree that what I want to explain is what happens about the anion. Then you do the analysis and say, there is resonance, and therefore it is not true. If I stay drawn in this way, if I move all the electrons there. Question if this is the situation, if again we have worsened the negative charge. What do you expect that a black hydroxyl has a positive or negative sigma of Hammett should have a very good negative sigma? That is the expect. Pet. Because it is worsening the stability of the conjugate base, and therefore it is behaving as a powerful electronic data, however. In practice, it has a powerful positive value. But not because of the resonance effect, but because there is an aesthetic effect that increases the acidity of the acid. And what is that effect? Something else that can happen there, because the hydroxyl group is quite Shuffle group is quite she-roxyl. Also to the acid. So how do we explain the value I'm going to give you from pK to A according to literature? And here I have it for the 2-hydroxybenzoic acid or salicylic acid is 2-10 97, that is. It is super acid. It is more acid than all the previous ones. And as it is so acid, one says, but as if I have an electrode according to Hammett. Yes, but now, as it is in an ortho position, has a certain aesthetic effect, a certain spatial interaction, that is an interaction called intramolecular chelation. That is, when something is in an ortho position, the values are altered by situations like this. Exactly. Very well then. What is happening there? We have there an intramolecular hydrogen bridge and increases or decreases the acidity of the carboxylic group. Increases it because that oxygen is like that. It is pulling the proton, favoring it to come out at some point. Therefore, the acidity, the conclusion is the acidity, increases the pK to a low, and that is for that intramolecular interaction. That is for an aesthetic spatial effect. And so with that, it is explained that part that is very fine of the Hammett descriptor, the electric attract, core effect, and well. Then we return to the problem. What is the problem that we had here? The problem is the following. We have this type of molecule with this QSAR equation that was found. that it was a quasar equation that allowed two things. First, this equation has allowed the development of modern insecticides. That is why I have this image. And secondly, it also allowed the development of inhibitors. Then I have the development of insecticide. Then it allowed the development of inhibitors of acetylcholinesterase. Acetylcholinesterase is an enzyme that is both in insects and in humans, and it turns out that at the level of insect, when we inhibit the acetylcholinesterase, the effect is so fast that the insect dies. It produces an instant neurological paralysis effect. In humans, the inhibition of acetylcholinesterase can be occupied peripherally by this type of derivatives that are acovalent, and particularly at the phthalmic level for the treatment of a condition called glaucoma, which is the increase in intraocular pressure that can be serious because it can cause refining detachment. Sorry, exactly. And it has another mechanism of action. Yes, the rostrum has a mechanism of action at the level of prostaglandins. This type of molecule has a mechanism of action by inhibition of acetylcholinesterase, intraocular, and that makes intraocular pressure decrease. And then the point is, regardless of whether we want an insect or inhibitor of acetylcholinesterase, this equation was found. Then this molecule that an acetylcholinesterase has a serine. This is very... And what is going to happen between the hydroxyl of very well, they're going to be in the tree. A nucleophilic attack occurs. We are going to have the loss of a group coming out of the structure, and therefore the enzyme is going to be inhibited covalently. A covalent link is going to be formed between the catalytic serine of the acetylcholinesterase and its serine residue, making it unusable said enzyme. This equation was found to use that the PC50 is equal to 2, 3 by sigma minus 0.348. This type of molecule is designed to act on the surface of the insect membranes where the acetylcholinesterase is concentrated at the superficial level, and it is needed to get a good insecticide. That is how the X in the aromatic ring is the part where we have to give the interpretation, and from there and give the mechanical interpretation, hopefully. Then what is required for the X to be an electrode or an electrode attractor to have a good insecticide? Perfect. Then we need a powerful electrode attractor. Ask why an attractor and not a donor. And now we go to the mechanism of action that I just told you, that consists of uniting covalently to a serine. If you have an electrode attractor, the phosphorus becomes more nucleophilic or more electrophilic if it has a group X that is removing electronic density. Very well, it becomes more electrophilic than if X is the electrode attractor. The electrophilia of the phosphorus atom increases. In that way, it becomes more oxophilic, and therefore it is easier for it to be united covalently to the residue of serine. And there is the explanation. Then the QSAR equation, is the descriptors that you occupy always have to give a mechanical explanation as far as possible. The descriptors QSAR have to avoid the following three conditions. The descriptors QSAR have to avoid first being what I known as collineal. We cannot have, for example, I already told you the other time, a cell of P, and also calculated by another algorithm, such as an L of P, not one or another. Or I cannot have, for example, as a descriptor, 2 multiplied by log P. I cannot invent a descriptor multiplied by an arbitrary number to improve the error, because when this happens, the error of the regression improves. We have to avoid all those descriptors that are correlated with each other. On the other hand, we have to also avoid irrelevant descriptors. And here I mean with this, they are all those that there is no way to correlate them with some mechanism of action. That is, without a mechanical correlation. If there is an absurd descriptor with a very abstract meaning unable to be interpreted humanly speaking, no matter how good the correlation is, we discard it because I cannot correlate it with a mechanism of action. Then, abstract descriptors, for example, if in the previous case they allow me to return the image a second. If here I would have said that we have an equation to use using the angular moment of the molecule as a descriptor, and a descriptor that can be calculated from quantum mechanics, and how I explained that the angular moment of the molecule generates a certain value of p infinity, I understand that it will cost a lot to explain the mechanism with a descriptor like that, although it is good. And the third situation, they have to avoid sparse descriptors if it is written. What does that mean? They are this point for abstract. They are situations in which the same value is repeated a lot, with very repetitive values. Example, suppose that you have a series already. Imagine that you have a series of 20 molecules, and of the 20 days, they are isomerous, and of the 20, the half are isomerous among themselves. Ask if they are isomerous, it means that the structure changes, but how will the molecular weight be the same? That is, they will have 10 molecular weights, equal molecular weight, 1 molecular weight, 2 up to molecular weight, 10. Then if you say, I want to account pi molecular weight as a descriptor moment, cannot, because it is sparse. That is, we have that 10 of those descriptors are going to have the same value. Then what contribution does it make? How it allows me to differentiate. Something does not contribute. Okay, we cannot occupy sparse descriptors. Now, again, it is a concept a bit abstract. I gave you a concrete example. This is seen a lot when it takes care of what is called topological descriptor. Stat. Many molecules have almost the same value of the descriptor, and in reality we cannot explain anything with that. And reaching this point, and the last one of the last descriptors that I have to explain to you, that allows you to compare molecular similarity, and that they help to cross several metrics, is what we had mentioned in past classes. That is called the Tanimoto index. Then taking advantage. Well, the Tanimoto index, what it calculates, or what let's say already proposes, is an index that defines a degree of structural similarity at the chemical level. The human eye is super relevant. When one is comparing molecules, a good trained eye helps a lot to be able to say if two molecules look alike or not. That works, for example, when we studied a technique that consists of replacing a group by another that is similar in physical properties, as that was called when you change, for example, a hydrogen by a fluid because they are similar in size. Exactly. And that is very good. Then the chemical I being some is very important in all this topic, but how quantitatively we have a number, and here the answer, the Tanimoto index, is defined as follows. The Tanimoto index. Y is equal to a coef. I am going to explain it divided by plus b minus c, and then that is the formula. But now I am going to explain what this consists of, and this would be the Tanimoto index for what thing to compare a molecule, A with a mol, equal to B, and I'm going to show you a free website where we are also going to calculate this. The Tanimoto index for two molecules, AB tells us the following first. If the Tanimoto index is 0, it means that the dissimilarity is absolute. That means that they are two molecules so different that they have nothing in common, and obviously, if we have an intermediate value, it means to a certain degree already of similarity, you will say, and for what it serves to you. Sometimes we want to find similar molecules, and sometimes the opposite later. When we see something of docking, we will see that there sometimes one wants the opposite, one wants to find molecules that do not resemble W's, that do not resemble W. One is studying under certain validation. Yes, because that is true. For it to be 0 not true, the value C that you see here would have to tend to 0, that is for it to be very good. This value C has to tend to 0, therefore, what is ABC good? We are going to do. Following that the molecule, so that this can be calculated, what we have to do is the following to be able to calculate the Tanimoto index. The strategy is the following. Obviously, you are not going to do it by hand, but the strategy is the following. The molecule is codified. The molecule is codified on the basis of bits. So we are going to call it on the basis of bits, and turned on and off, turned on. Between parentheses, that is equivalent to a 1, or turned off, that is equivalent. The molecule is codified on the basis of bits, turned on or off, how many. The two most common ways to calculate, we can transform the molecule in 1024 bits, or in 2048 bits, or the two most common. I know that this one says it looks like something computational. Yes, but the idea is a little more concrete. Look. Let's go here. And if it has to do with that, all those areas are related. And Tanimoto is one that I say as the basis for all that already continues. Very good observation in theory. Yes, because if one has defined what each bit is equivalent, and two in terms of fragments, one should be able to go from there to what is called the smile of the molecule. The molecule represented in a linear way, but we are only going to go to the number that interests us now. Then L. Look at the example. We are going to say that the value A are the fragments of A itself. That is, fragments. Vice versa, B means the fragments in B and not in A and C are the common fragments, that is, in A and B. Then it seems a bit like the theory of together things that are in one, but not in another, and finally things of intersection. Then you will see well, and how I transfer all that, how it converts a molecule into a binary code of 1 and zeros. If you have ethanol, for example, if we have the ethanol, we would already have this molecule like this. And there, it is not true. And we have that this ends with an OH. Then I have that this is a H, is a methyl, H3, This is a sheet 2, and there ends up an H. Then, if I want to compare the ethanol, for example, with a molecule similar to H3 sheet H, and instead of having there or ash, let's put it in H2, then these two molecules are similar. The two are polar compounds. But how do WW2 are polar compounds? A given number of structural similarities, well, of this molecule are not true. They would be a present methyl, a present methylene, a present hydroxyl, present a carbon-carbon bond. Look at how things are being defined: a carbon-carbon bond, a carbon-oxygen bond. And then that would be the fragments not true that it has. And I think that I do not have anything else not true with the most common groups here. In the second case, the B here, then B, has also not true. A methyl group has a carbon-carbon bond, has a nitrogen-carbon bond. And there I do not know if I have any 1, 2, 3, 4. There is something missing here. Has an amino. Has an amino not true. And then we have all those particular situations. Ask, what are the common ones? Then I am going to highlight the common fragments and the H2 in the carbon-carbon bond up to there or not. And then we have that there are 3 common fragments. 3? Okay, 1, 2, 3. Then we go there. 3 common fragments. How many fragments are and the HO and the KIO, then notice that in reality they have more things described because they have to reach 1024 descriptions. Understand, I am describing 1, 2, 3, 4, 5 things, no more. So give me a very approximate value, A. It could be, for example, say, when we have carbon sp3 carbon, it is understood. And so each little thing in particular is decomposed into a 1 or a 0. And then for A, they would be 2 things. For B, how much would they be? The dots. How much would they be? Zami must also be 2 things, not true. Then they gave me a value that does not serve us. That is, I am very approximate, but the idea is understood, because here, how much is this going to give us? This to 4 minus 3 to 1. That is, it's say. Stat they are. They are not, because the maximum Tanimoto is 1. This is giving me that it records appeared and it is understood. But the idea in the background is that it is to divide the molecule into 1 and in zeros be count. Zay, it does not give us such a high number because we need to describe more things we need to describe. For example, carbon sp2 oxygen, carbon sp2 nitrogen, carbon argon, sp3. Sorry, between them. Not true, a carbon sp3 with A on J. Trogen sp3, carbon sp3 with an oxygen sp3, etc. I see, etc. We are going to go to this website that I have here, then a second, so that we project the screen is already projected. Enter, we go to this website of similarity, and here we can calculate the exact value. And then we need to calculate the structural similarity already. But I need to add compounds. There, yes, add compounds. And I need here the ethanol smile of the ethanol good. Ethanol is carbon-carbon oxygen. And I need the min, E. The mine is carbon nitrogen. And they are super simple smiles. So the smile is a notation in the line of the molecule. And we are going to submit. and wait for the value now. And I have two compounds. Yes. Yes, of course there is an error, and very well, if we have an error, allow me to see if I can rectify this, maybe. With capital letters, carbon, carbon, oxygen, carbon, carbon, nitrogen, we go again. And there are the others that now, if it is not true to see this, for example, it is fine, and of course already perfect. I saved the previous ones if now, but what we need now is that they calculate us a good find. There we already have the compounds added. We are going here, we are going to see if and interpret them like this, exactly my interpretation very well. And then it says, select. Where is the ethanol? This is good. And that is good. And the good. And the good amine, is this okay? We already have those two. Let's see if it has the little button out there. I myself again, the same thing to see this and that. We give it a second, and up there, of course, it is loading here. I am going to try, because I remember that it was quite automatic. This I do not know why now it is not giving me the value we leave here, and it says 4 compounds. And it is not giving me the value. There we go here. They are. I think that if that can be, as it generates some problem there. If better, I am going to eliminate those that are wrong here. I have to eliminate them in some way. It seems extremely strange to me not to be able to. Not be able to end in a simple way. Let's do something. Let's draw it again. I'm going to get out of here. We're going to close, and open the page again. And load another B. Here, Thank you for watching. It was automatic. You know that in the website, it is not working because as such, when selecting two compounds, it generates a similarity value of Tanimoto that is not giving it in this case for some reason, it is not loading it for us, and it is not the only way. I always try to show the simplest for categorical effects. One can calculate this. We have done it automatically with a Python script, and there you can throw thousands of molecules, and it delivers the value automated. Okay, so for practical effects, we are going to leave it there. We are going to leave the issue of the Tanimoto there already well. Then returning here to the tip, we see what we had left. We have that, and there we would have the explanation of the constant of James. And it says here, the steric factor, or the steric factor of Taft, we already have that the steric factor of Taft is a measurement both of the VEO luma that a molar volume substitute has, because it is a measurement of the volume of the size, as of its finally of its diameter. Observe the following to be able to measure. Yes, tell me. Thank you, of course. We have to maxim. Exit there. If thank you very much, then the steric factor of Taft is its S, is a measurement of the molar volume. This is one of the ways to estimate the molar volume. The other way today is through the molar refractivity. We are going to put the steric factor of Taft, that is this, that is being shown here, the empirical reference system, as this is measured, which is no other thing than the hydrolysis of a reference ester. And the reference ester is when X, what is connected here, is a methyl group. That is, this would be a methyl. The methyl propano then has a methyl group as a reference here. The hydrolysis of the ester is carried out in the acid medium. Therefore, it is a reversible hydrolysis. We can calculate a constant of hydrolysis then at I. It's in the acid medium to be able to calculate the hydrolysis constant. What happens if I do the hydrolysis in the basic medium? That will happen. The process will be reversible or irreversible, and hydrolysis is based irreversible. That is why the hydrolysis to determine Taft is defined in the acid medium to have a reversible process. And if we have a reversible process, we can calculate a reversibility constant. The reference ester is A. The constant of Taft is defined in this way. The logarithm of the constant when the interest group is less when there is nothing. That is, when there is the methyl question, what happens if the group X that I want to determine is greater? Example, I want to know what is the value of a benzene, and I put something big. A benzene, the hydrolysis will be easier, more difficult. If here I have a large voluminous substitute, more difficult, and this value is larger or smaller. The case of X of X. If we have a voluminous substitute, is not that here we are not evaluating acid, but it is the hydrolysis. And how is it going to be? Then this value of constant hydrolysis, if my voluminous substitute is going to be easier, more difficult to hydrolyze, more difficult, because there is a more voluminous substitute. And therefore, more difficult, not true. Then the value will be positive or negative. Negative then. This was more difficult to interpret. Then we are going to say that if the value is negative, then we have large volume substitutes, voluminous substitutes. If the value is positive, they are small substitutes. I. T is a measure the steric factor of Taft, then of the steric resistance that a substitute offers, of its size, of the spatial disturbance that it offers for this process, empirically measure. This is already laborious because we would have to measure many different groups connected there, and there are tables with the steric value of Taft. But the other way, a little more modern today, to measure molar refractivity, to measure the steric factor, why? It's through the use of molar refractivity. That is, molar refractivity is the molar volume multiplied by something perfect that was not true mass. The molecular weight divided by the density is the molar volume multiplied by size here, the refractive index in this formula, which is a descriptor that shows us the ease to polarize then molecules with a high value of molar refractivity. A high molar refractivity implies a high volume and also impotile. Is and is to polarize. Until that's a later anodoctrin yes to turn, it is to polarize. A high polarizability. That is the way then to measure molar refractivity.